Okay, this is problem 8.3. It's a nice, good example of a friction problem. We're supposed to determine whether the block shown is in equilibrium and then find the magnitude and direction of the friction force when theta is 40 degrees and P is equal to 400 newtons. Okay, so what do you have? Well, you have this block, so there is going to be a normal force pushing in this direction, right? And there's going to be a friction force. And here's the key. Is the friction force going to be this way or this way? Honestly, we don't know. We have to figure that out, right? But there's going to be some sort of friction force. This is a normal force. So it's going to be one of these. It's not going to be both, obviously. And you're going to have the force down here of the 800 newtons and the P coming off here of P. Okay. So the way I like to do this is I just find it a little bit easier. I say that and it's not even obvious that it's that much easier, but I'm going to write this free body diagram flat. Okay. So my normal force is going to be there. So my weight is going to be off at this angle here. It's going to come down here, and that's 800. Whoa, sorry, that was weird. Stop that. 800 newtons. Okay, just ignore that. And this is at 25 degrees. And then this P is going to come off here. This is P of 400. And this is at an angle of 15 degrees. Okay, so that is our free body diagram. That's what we're looking at. So notice I didn't draw a friction here yet. That's on purpose. So let's do this. So let's say, what is the x component of the 800? The x component of the 800 is what? It's going to be 800 times in this case sine of 25, and that is equal to 338, and that's going to be off in this direction, right? That's this portion of the force right here, and then there's a portion coming down right here. Okay, and the x component of the 400 is going to be 400 times cosine of 15, which is 386. 386 going off in that direction. Okay. Okay. So 386. So that means that there's a net total, if you take the difference between these two, of 48 newtons wanting to go this way. So why is that important? Well, that means that the friction is going to be in this direction, right? Because it's trying to resist force, and if there's a net desire for this thing to go go to the left, the friction has to resist that. So there's 48 newtons of force making this thing want to go up the hill, if you will. And so now we've got to figure out which direction. So therefore, the friction has to be in this direction. So now, what's the next step? Well, the next step is to decide, is this moving or is this not moving? Well, how do we know if it's moving? Well, assuming it's stationary, if it has had enough friction to overcome the impending motion, then it'll start to move, right? So how do we figure that out? Well, we figure out what's the maximum friction that it can resist and still stay stationary. So F, this is jumping around, sorry, max is going to be the normal force times mu sub S, right? So what is a normal force? Well, we got to figure that out. So we're going to come over here, we're going to take sum of the forces in y is equal to 0. And so the normal force plus P, the y component of the P, is equal to the y component of the 800 Newton down, right? So normal force plus 400 sine 15 is equal to 800 cosine of 25. And that tells us, therefore, that the normal force is equal to 621.5 newtons. So therefore, my F max is 621.5 times my mu sub S, which in this case is 0.2. So my F max is equal to 124 newtons. So again, what is this F max? That is the maximum amount of friction that the maximum amount of force that the friction can resist. So if there's 124 newtons going up or down the hill, or anything less than that, then I'll be stationary. If anything above that, it'll start to move. Okay. So is that what we need to find? No, it is not. So we need to determine whether the block shown is in equilibrium. Is it in equilibrium? Well, there's 48 newtons trying to push it up the hill, and it's going to resist 124. So yes, in equilibrium. Okay, so that's the first answer. And then find the magnitude and direction of the friction force. Okay, so what is the magnitude and the direction of the friction force? Is it 124 newtons? No. 124 newtons is the maximum that it can resist. But it only needs to resist 48 newtons because there's only 48 newtons trying to push this thing down. So F is equal to 48 newtons. And which direction? It's in that direction. Or when you kind of rotate things around, it's kind of in that direction. So the frictional force is 48 newtons going down the slope. And that's its resisting movement going up the slope.